All right, Unit 1, Topic 1. All right, Unit 1 is all over function analysis. We're going to learn a ton about how to look and analyze and talk about functions. So this first topic is function properties, and there's lots of properties about functions, and we're going to slowly learn all of them. But the first is domain and range as well, but the big focus of this is going to be domain. So let's talk a little bit about what that is. So make sure that we first understand what the heck a function is. I mean, how are we going to spend a whole unit on a function if you don't know what a function is? So a function from a set D to a set R is a rule that assigns to each element in D a unique element in R. So in a lot of textbooks, you open it up, they draw a little picture like this. So you have set D, and then you have another set of numbers R, and a function takes an element from D and assigns it to a unique element in R. So the key idea is that each input is allowed one and only one output. So let's just say that one of the numbers in set D is the number 2, and when we plug number 2 into the function, let's just call it f for the function, right? We plug number 2 in, and the output is 17. Well, what that means is that when we plug in 2, we only get 17. There's nothing else that we can get. We don't, blink our eyes and plug in 2 again and all of a sudden mysteriously get 25. No, you get 17. It's the one and only one output for 17. Now, 2 could go nowhere, or, there could be a value in D, let's just say 5, and it goes nowhere. It doesn't go at all. That happens. That is possible. You could also have a value also go to 17. Like maybe the number 3, for some reason, also shoots you to 17. That is totally possible. But the key is that every input, whatever input you have, can only go to one and only one output. Now, we call the set D all of the input values. This is the domain of the function. So the list, the set, the interval that contains all possible input values is known as the domain. And the set R, or all of the output values, the interval, the set of all values that you get out of the function is known as the range. So here is a very simple example of a function. So first off, on the left-hand side here, we have what is read as f of x. It's actually read f of x, okay? You could also use y in place of it. Y is a typical output value on a coordinate grid. When we make a graph, we have the x-axis and the y-axis. So the x is the input, the y is the output, which again, in function notation, we use this f of x symbol. And basically, it's a rule. Remember, it said that it's a rule, right? Functions are a rule. So this particular function has a very simple rule. You take any number you want. Take any number. You have to follow the rule. The first rule is square it. Then multiply it by 2. Then add 3. So if I were to ask you to evaluate f of 5. All right, so what this tells me to do is I got to follow the rule. The first thing I'm going to do is plug in 5. Okay, great. Square it. Okay, great. 25. Times it by 2. Fantastic. 50. Add 3. 53. So my input of 5 led me to my output of 53. And if you plug in 5 again, you'll get 53. If you plug in 5 again, you'll get 53. If you plug in 5 again, you'll get 53. If you plug in 5 again, you'll get 53. You won't get anything else, meaning for that one input, there is only one output, 53. Now check this out. What if we did f of negative 5? Negative 5, if I plug it into this function, negative 5 squared is also positive 25. Times 2 is 50, plus 3 is also 53. So we notice that we have 2 inputs that both lead to 53. That's totally fine. That is totally allowed. What is not allowed is for me to magically plug in 5 and then get 17. Wait, you can't have 5 go to 53 and then 2 moments later go to 17. That cannot happen. That's not a function. So that is kind of the idea of what a function is, and hopefully that was nothing more than a recap. I look at functions as a machine, and there's all kinds of math: addition, subtraction, multiplication, division, negatives, positive, parentheses, square roots, squaring, all different things that can happen in a function. But at the end of the day, a function is like a machine. You take an input value, which we typically call x, you plug it into that machine, and something is done, whatever it is done, and then out becomes an output. And again, we call that output traditionally y when we're working with an xy axis, if we're going to make a graph of it, or we can now use this notation, function notation f of x. All right, so let's talk about one more function just to try to give you guys one more example. Here's another function. The rule is take x and square it, take x and times it by 6, add those together, and then add 5. So if we want to evaluate a function, we could, plug in a number. So we could plug in 2. And you know what? You guys are honor students, so take your time, show whatever work you need to. 2 squared is 4. You guys could do that in your head. 6 times 2 is 12. You could do that in your head. Now you got to add these together. 4 and 12 is 16 plus 5 is 21. Boom, easy. There's your output. So 2 took me to 21. Awesome. All right, now, you could also plug in other variables, right? You don't have to use x. I could use a w, for example. I could say, hey, what's f of w? Well, w squared plus 6 times w plus 5. Okay, great. So I still don't know what w is, but it doesn't mean that I can't just replace the x with w. We could even plug in, fictional things like lightning bolt. And we could do lightning bolt squared plus 6 times lightning bolt plus 5. Now, I have no idea what a lightning bolt is, but you could certainly plug it into the function. Now, it's not a number, obviously, but maybe it represents a number because maybe somebody whispers into your ear, hey, lightning bolt equals -3. Well, then all of a sudden you could plug -3 in, okay? We could also plug in multiple things. Like maybe we want to plug in x plus 5. All right, so now it's a quantity, right? X plus 5 is technically one value. It looks like 2 values, x plus 5, but if somebody told you what x was, then you would add 5, and you'd really only have one value. So x plus 5 is one number. So you just got to be careful to use parentheses when you plug it in. So we have x plus 5, whatever that is, squared, plus 6 times x plus 5, again, whatever that would end up being, plus 5. And then you could actually do some math work to clean that up. You could multiply out x plus 5 squared, and you could just shade the 6, all that fun stuff. But we can evaluate functions with numbers, other variables, or even expressions. All right, now we also need to be able to look at functions graphically. So here is a function, and I'll just define it as f of x. I don't really know exactly what it is, but I have to see a picture of it, right? So, we could have a algebraic form of a function like we saw in the last example, or we could have a picture form, a graph of the function. But I could still do some evaluating here, right? So I could say, all right, what's f of 2? And you're going to look at the graph, you're going to say, okay, well, when x is 2, it looks like the output is, I don't know. You have to do some analyzing here, some estimating. Maybe you estimate 1/3. Okay, great, awesome. Obviously, there's some easier ones like f of 1. Well, there's a clear, very simple dot at 1 there. I could ask you, hey, what's f of -1? And it looks like there's a dot down here at -3. Okay, now what about domain and range, right? So a domain, remember, is a list of all the values. And the range, all the input values, excuse me, and the range is a list of all the output values. So if I'm looking at this, remember these arrows show that this is going down and left forever, and this arrow means it's going down and right forever. So in terms of the input values or the x values, there appears that there is no issues at all. All values can be used. And when we represent the domain, we use a D for domain, or the set D, and all values would be -infinity to infinity because, even though I don't see -10 on the graph, it is somewhere over here, and the graph is going to correspond somewhere way down here. Now, the range is the set of output values. Those are the y values, and we do see that the highest y value is 1. There is no y values greater than this 1 right here. And, it does go down forever. These arrows, again, imply that it goes down forever. So the range would be -infinity to 1. And I'm going to put a bracket on that 1 because you are allowed to equal 1. So the range is, again, representing what y values can you get out. And because these arrows go down forever, right here and right here, any y value starting at 1 and going all the way below. But again, remember, we do give interval notation left to right. So we definitely want to start the interval towards -infinity. That's to the left, or actually down in this case, and then towards 1. All right, we're going to look at some more examples of graphs towards the end of the video. All right, so how do you find domain? Well, there's 2 ways that you need to be able to find the domain of a function. You need to be able to look at it and figure out the domain algebraically using your algebra skills. You also need to be able to look at a function and understand its domain just by looking at the graph, kind of like I just did. Now, no matter what, you have to give the domain in interval notation, which remember is an interval of x values going left to right. You got to make sure to use brackets when you can include numbers, parentheses when you cannot, all that fun stuff. Now, when we begin our modeling unit, this is what we're going to do, and again in a little bit, this is unit 2 is our modeling unit. Just note this, that oftentimes the domain is restricted to be something specific for a relevant problem, okay? What I mean by that is when we're working with real-world problems, sometimes the domain has nothing to do with the graph or the function. The domain has to do with what is possible in that real-world scenario. And if you don't understand that right now, don't worry about it. We'll talk a lot more about that in the later unit. All right, so there are 3 big domain issues that you need to be aware of, things to think about when you're looking at a function. Number 1 is square roots. When you see a square root, you're only allowed to have values greater than or equal to 0 inside of that square root. You cannot have negative numbers in a square root. They are not in the domain. The denominator of a rational expression cannot be 0. So when you're working with a fractional or a rational expression or a rational function, you could never ever have a 0 at the denominator, so those values are not in the domain. And lastly, the value on the inside of a logarithm must be strictly greater than 0. You're not even allowed to have a 0 inside of a logarithm. So inside of a logarithm could only be numbers greater than 0. So these are 3 of the big issues you have to think about. So right now, at the very beginning of this, if you don't see a square root, you do not see a variable in a denominator, and you do not see a log, for the most part, honestly, the domain is going to be all real numbers. Now, I'm not going to say that that's 100% always going to be true, but for right now, it probably is. So remember, all real numbers means all values at the far left, negative infinity, to the far right, positive infinity. But if you do see any of these issues, square root, rational expression, denominator, or logarithm, then you need to consider the domain. So, one other big piece of information is that all polynomial functions have a domain of all real numbers. Again, check this out. No square roots, no logs, no variables in a denominator. So this automatically has a domain of all real numbers. All polynomials have a domain of negative infinity to infinity. Now remember, what's a polynomial, right? Well, it's in form x to the n plus x to the n minus 1 plus x to the n minus 2, dot, 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 right? No square roots, no logs, no variables and denominators, just a variable with powers, okay? Like the one we see here. All right, so let's take a look at a square root function. Let's talk about how to find the domain. Now, we do know the key here is that the number inside, right there, cannot be less than 0. So the domain is what you can be. So let's not be negative. Let's be positive. What can I be? Now, notice the 3 on the outside has nothing to do with domain because it's not inside the square root. The negative 7 on the outside, again, is not in the square root, so it's nothing to do with domain. Here's what I know. The number inside the square root, x plus 2, has to be, again, I'm thinking positive, right? What is it allowed to be? It's allowed to be anything greater than or equal to 0. As long as this number in here is greater than or equal to 0, you are in the domain. I'll give you an example of a number that doesn't work. Negative 7. If you plug in negative 7 for x, you're going to get a negative 5 in a square root. That's going to make the whole function not possible. So that is why negative 7 is not in the domain. But as long as the number inside, which is currently being said as x plus 2, is greater than or equal to 0, we are in the domain. So all we got to do is solve this. X is greater than or equal to negative 2. There's your domain. Now we do have to put this in interval notation. So this means x could be any number starting with negative 2, going all the way above as high as it can. And I'm going to put a bracket on that negative 2 because I am allowed to equal negative 2. Again, zeros in square roots are okay. So the domain is any number at negative 2 equaling to negative 2 or anything greater than. So make sure you remember interval notation. All right, here's one with logs. So let's remember we got logs. So logs are similar to square roots. The 3's on the outside doesn't affect domain. The 8's on the outside doesn't affect domain. The only thing that I have to worry about is that this number on the inside has to be greater than 0. So again, don't think about what it can't be. What it can't be is 0 or negative, but the domain is what we can be. So 3x minus 5 has to strictly be greater than 0. So all we got to do is solve this, which is pretty easy to do. And x is greater than 5/3. As long as x is a number greater than 5/3, you are in the domain. So the domain is a parenthesis on that 5/3 because I'm not allowed to equal it, all the way towards infinity. And again, if I plug in 5/3, 3 times 5/3 is 5, 5 minus 5 is 0, you're not allowed to have zeros in logs. And it doesn't matter what the base is. It doesn't matter. If you see a log, cannot have zeros or negatives inside of it. It can only be greater than 0. All right, here's another example where we do see a denominator, and it has to have a variable in it. Remember, if you just see a denominator, like if you just see a 1/3, that's not a problem, right? It's when there is a variable in the denominator. So here's what you got to be concerned with, is that I'm just simply not allowed to equal 0. Negatives are okay. Don't care about a negative in the denominator. Positives are okay. Don't care about positive in the denominator. I care only about the fact that the denominator cannot be equal to 0. So once again, I'm going to say 2x minus 6 cannot equal 0. And I'm still going to solve this. So I get 2x does not equal 6. X does not equal 3. So there I go. Every number works. The only number that I'm not allowed to use is 3. Because if I plug in 3, I'm going to get a negative in the denominator. And a 0. I'm so sorry I said that. A 0 in the denominator. And you just cannot have a 0 in the denominator. Negative's okay. Positive's okay. No 0. So how do I write the domain here? Well, this basically means that if I make a number line, there's simply a big open hole at -3. Every number below it works. I'm sorry, +3. Every number above it works. It's just negative. It's just 3. It's just 3 that doesn't work. I apologize. I kept saying -3. It's just 3. It doesn't work. So to write the domain, it's actually very simple. You go from -infinity to 3. You take a quick break. You step over 3, and you continue on towards infinity. The u is just a union. It's the joining of the two. So I'm going every number from -infinity to 3, every number from 3 to infinity, but I got those parentheses on that 3 because I'm taking a break, a big open circle there, only at 3. So that is how I express the domain there. All right, now let's look at a couple of what I call double whammies, okay? These are questions that have both fractions and square roots. Wah, wah, wah. So you just got to really think here. You got to open up your brain and think logically. All right, let's handle the square root first, right? I know that x plus 5, a number inside of a square root, has to be greater than or equal to 0. That's the rule. Inside of a square root, you're only allowed to be numbers greater than or equal to 0. But wait a minute, here's the problem. Yes, I'm allowed to have a 0 in the square root, but because that square root's in the denominator, I'm not allowed to have it equal to 0. So the square root allows zeros, but the denominator does not. So I'm simply going to take away the or equal to sign. Basically, the x plus 5 has to strictly be greater than 0, making the square root happy, and it's not allowed to equal 0, making the fraction happy. So x is greater than -5. So the domain is a parenthesis on the -5 all the way towards infinity. If you plug -5 in, the square root says, I don't mind there's a 0 inside of me. Oh, but wait a minute, the fraction says, I do mind that there's a 0 in the denominator. So that's why you cannot equal -5 in this case. All right, here's another example, but notice this time the square root's in the numerator. So the x plus 8 has to be greater than or equal to 0. You're allowed to have zeros in numerators. That's not a problem at all. 0 divided by 5 is 0. 0 divided by 7 is 0. Zeros in numerators are okay. So once again, I see a square root. The rule with square roots is that the inside can only be greater than or equal to 0. But I have a second problem. The x minus 4 in the denominator is not allowed to equal 0, which means x is not allowed to equal 4. So I have to deal with two problems. The first problem is that x cannot equal 4. The second issue is that x is only allowed to be greater than or equal to -8. So any number starting at -8 going towards infinity works, but you got to skip 4. So how do I express that as a domain? Well, I'm going to start at -8 because that's all the way to the left. Put a bracket because you are allowed to equal -8. And then you're going to continue until you hit 4. And then you're just going to simply step over top of 4. That's it. So if you think about a number line, here's -8. I'm allowed to equal -8. And I'm allowed to be anything greater than negative 8. But at 4, I got to leave an open circle because you're not allowed to equal 4. So to express that interval notation is you just have to start at negative 8, go to 4, step over 4, just kind of take a quick break at 4 and go on towards infinity. Pretty simple. All right, let's take a look at some graphs and let's ask you some similar questions with this graph. So if I said with this graph, hey, what is the domain? So say, all right, what's the domain? Well, I do see a dot right here starting at negative 9, and there's nothing before negative 9. I don't see any part of the graph. There's no arrows that indicate it's over there. So it looks like the graph starts the domain at negative 9, and this arrow does mean it's going down and over. Now, it might take a while to go over, but it is going over. So that technically means that any number to the far right works. Now, a lot of kids say, well, no, it's going down. Yes, but for example, if you think about 50, way over here, the graph does exist at 50. It's just way down here somewhere because this graph is taking its good old time, not only going down, but to the right. Now, what about the range? Remember, the range is the y values. So when we think about the y values, we think about starting down the negatives. This graph is going down forever, so the range starts at negative infinity, but it does peak right here. Notice that there are no values above 9, no values whatsoever above 9. Y values, I'm talking, the y values. So that means that the range stops at 9. So the range or the outputs are negative infinity all the way to 9. All right, here's another. This is actually a square root function. And again, we can see by looking at the graph that the domain is starting at 1. There's nothing before 1. And we're allowed to equal 1. We're going to go towards infinity. Now, again, you could prove that with what we learned earlier. Remember, inside the square root, the plus 2 is outside. It doesn't affect the domain at all. The x minus 1 inside has to be greater than or equal to 0, which means x is greater than or equal to 1. Hence why my domain starts at 1 and goes towards infinity. Now, the range is the y value, so I think down to up, right? So the range doesn't start until a y value of 2, and it looks like it's going to go on forever. Remember, not only is this arrow going to the right, it's also going up, so that means the range goes up forever. So that's it. So make sure that you could find domain by looking at a function's actual algebraic function. Really 3 big things to worry about: square roots, logarithms of any base, and rational functions where there's a variable in the exponent. If you quickly go back and look at any of the problems I did where we had a variable in the denominator, I think I said exponent a moment ago, I'm so sorry, in the denominator, remember the numerator doesn't bother me at all. The numerator is allowed to be any number. Numerators, there's no restrictions on them. It's denominators that simply cannot be 0. But be careful for the double whammy because as you see in this green problem, the numerator, because it has a square root, now it's restricted to only being greater than or equal to 0 in terms of what is inside that square root. And then lastly, make sure you can look at a graph and identify domain and range by looking at a graph as well. All right, guys, pretty easy. We'll give you some examples to practice. Good luck.